Good morning, guys. So, we are going to start our discussion on forces today. So, we are in chapter 7, section 1, which starts on page, 407. So, go ahead and open up your textbooks to 407. Take a moment, pause the video, and work on the engage your brain. Answer those two questions if you didn't do it already yesterday, which you should have. But on Friday, but I know some of you never opened your textbook to do this. So do that now. Okay, so what is a force and how does it act on an object? So forces are really, really simply put, simply a push or a pull on something. So, yes, when you push on somebody or you're pulling a wagon or you're kicking a soccer ball, all of those things are forces. And they have special names for those types of forces. But then there are these really amazing forces that we don't even really think about, and some we can't even see. But simply put, that is what a force is. A force is a push or a pull. All forces, okay, have a size and a direction. All of them. They all have force. They all have that. Okay. Now, you may have heard the word force, like don't force the issue or things like that in conversation. But that still is a push. Like you are pushing somebody, you're pushing that issue. So, or, oh, wow, that team is really a force to be reckoned with. Again, it is still a push on you. Like you have to mentally and physically prepare for that force that's coming at you, whatever that team happens to be. Okay. So a force is simply a push or pull. All forces have a size and a direction. A force can cause an object to change speed. It can change direction. And all of these things are relative to the other things around. And usually I don't like to use generic terms like stuff and things. But in this case, it literally is anything other than that object that is currently being affected is the stuff that it is in relation to. Like I know something is moving because I see it going past things that aren't moving or aren't moving as fast. I can tell which direction something is going because it's passing things that are there. And those have names, and those other things are referred to as reference points. When you're driving down the road, you know you're moving because things are moving past you. Okay, now sometimes things can look weird and you can be like, oh my gosh, it looks like we're moving, but we're not because other things are moving around us. It's so odd. You know that you're traveling faster than this car because you're passing that car. You know an airplane in the sky, you know an airplane is moving because when you start watching it, it's on the left side of the field, but by the time you look up again, you have to turn your head to the right and it's over there. So even though it's really far away and it doesn't look like it's moving very fast, but it's moving like hundreds of miles an hour, you see it moving, see it moving compared to what's called a reference point. And a reference point is when an object changes position over time relative to that thing. Okay, that object is in motion. My mouth is in motion and you can see that it moves, and relative to the rest of my face and stuff. So that is simply what a reference point is. And so that's why I said sometimes we are going to use generic terms, things like that, because it is literally, if I'm kicking a soccer ball, then you know the soccer ball is moving because it's literally moving past every single blade of grass. It is moving past the other players on the field. It is moving past the sideline. Like, it is moving past everything that your vision sees it next to. So, sorry, my daughter was texting me. So I was looking at that real fast. She's at school today. I'm so excited. We're trying this out. We'll see how long she can make it. So when you see an object in motion, you know that some kind of force is at play. It could be one force, it could be multiple forces, but some kind of force is at play. Okay. We measure forces in what is called newtons, and it's used with a capital N. So you'll see the number and then an N. So newtons is what we measure force in. And you'll notice later this week, you're going to use what's called a spring scale for a lab. And you're going to realize that the spring scale, you're like, why are there N's on this? Like, it's a scale. Aren't I measuring mass? And you are measuring the mass of something in newtons, because when you're measuring not the mass, you're measuring the weight. You're going to be measuring the weight of something. And weight really has to do with gravity, as you learned in the gravitational video. And so when you're measuring something hanging, you're actually measuring the gravitational force on that object. Okay. And forces only exist when there's an object for them to act on. So friction is always at play. Okay. It's always there. But whether it's like actively participating on an object also depends if there's an object there. Okay. Like, if I kick a soccer ball across the soccer field, friction is at play because the friction is what is causing the soccer ball to slow down. But as soon as I pick up that soccer ball, there's no longer friction with the grass. The friction now comes into play with me holding the soccer ball. So it kind of changes and moves, and sometimes is at play here and sometimes is placed somewhere else. Again, gravity. There's a reason that is called weightlessness in outer space. It's not really weightlessness because the planets have gravity and they are affecting the objects. But you'll see as we get along, that as you move further away from an object, you have less force on that object. And eventually you'll move far enough away from the Earth that the Earth's gravitational pull will no longer affect you. But does that mean that suddenly Earth has no gravity? No, absolutely not. It just means that it doesn't, it's just not affecting you. And not all forces cause movement. Right now, every single one of you, if you are in your chair, is experiencing a force. You are sitting in your chair. That is a force. You are putting a force on that chair, and the chair is putting a force on you. And yet you are sitting still. Okay, so that is also forces. So forces can act in one of two ways. It can act directly or indirectly on an object. Okay, so if you look at your picture on page 409, okay, there is an airplane in that picture. Okay, and it's not always easy to tell what force, what's exerting a force and what is being acted on by a force. That can sometimes be a little bit difficult, especially when we get into Newton's third law of motion, where every action has an opposite and equal reaction. That is not always easy to see, and we'll talk a little bit about that in a second. In a few minutes when we get to that point, okay? So when one object touches or bumps into another object, we say that the objects are in contact with each other. So right now, you are in contact with your chair because you are touching it. If your feet are on the floor, you are in contact with the floor. And then if you are holding a pencil, you are in contact with that pencil. Okay. So those things, um, that means that you have a direct contact with those objects. So, a force exerted during contact between objects is called a contact force. There's also non contact forces. You do not have to be touching the object to feel the force or have the force affect you. There are friction is an example of a force between two surfaces. I mentioned this early, friction. You might think, oh, friction is awful. We're going to do some like this activity is really, really simple. We're going to just kind of show a couple things, but just think about it. I don't know if you've ever been washing dishes and you had to take like the lid off of something, like you're trying to take the lid off your water bottle, but your hands are soapy and wet. And you're like, I can't get this lid off. And you have to like call your parents or your sibling over and be like, please open this water bottle. My hands are all wet. In that case, you're like, I really needed friction. I didn't have any friction. The soap on my hands made my hands less frictiony, and so I couldn't open the water bottle. But your sibling or whatever, your grandparents opened the container because they had friction. Their hands were dry. And so that's why there's sometimes those special tools that help grip jar lids to help open them and so on. So we have two types of friction. Friction is helpful and friction can be harmful. And I said, we'll kind of explore some of these. Friction is a really fun one to kind of go through. So we'll probably play around with it at the end of this section, just because we don't really focus a lot on this as a force in any of these sections, but it's one that is so important because if you didn't have friction, you couldn't walk. Okay, you wouldn't be able to sit in your chair. You wouldn't be able to hold your pencil. There's so many things you could not do without friction, but at the same time, too much friction can be harmful for stuff. So there's static friction and kinetic friction. Static means to be still, pretty much. So static friction is the force that resists the start of what we call sliding motion or even like a rolling motion that are between two surfaces. So think about your book. If you guys have your book on your desk right now, create a little bit of space and just kind of gently push your book on your desk, just gently back and forth. It's probably really simple to move your textbook. Now, if you take a minute and you take everybody's textbooks and put them in a big pile and put all the books in a big pile and you were to try to push it, you can still do it, but it might be a little bit harder to get going. And this is static friction because what's happening is as you have more mass pushing down on the desk, which is creating friction. So friction, there is always a little bit of space between the objects. And there's always these little grooves and little hills and valleys between two items, things. Again, it could be literally everything. Okay. And those catch on each other. So you pushing your book, your desk and your book are pretty smooth items. Okay. They both have this you can run your hand over them and they feel smooth, right? But if something were to be rougher, then it would be harder to push your books across it because it would be rough. So sometimes carpet might make it a little bit more rough. Uneven ground makes it rough. So now take your hands, put them together, and rub them really fast. For just a few seconds, rub them really fast. And you might notice a couple things. One, you can hear it. And two, your hands may be getting a little warm. Okay. And that is because even though your hands feel really, really smooth, your fingerprints have ridges. Your entire hand, all of your skin have ridges. It's what gives your hands a grip. But that's also what causes friction. It's what allows you to open a jar lid. If you did not have those ridges and valleys in your hands, you would just slide right off of those jar lids. And you notice that there are some jars, and some jars are better at this than others, but the lids have kind of ridges around them as well. Sometimes those ridges can hurt. I swear sometimes trying to open like a 2 liter bottle of something or whatnot, especially the ones with the really little ridges, like you're like, I'm going to cut my hand. This is so rough. It's so hard to open this. And then some you might have a hard time opening because it's a lot smoother and the ridges are more wide. But those ridges are there so that there is a friction, so that the grip down your hand, all the little ridges on your hand, has ridges to kind of bump up against and create that, start off with that static so that your hand stays on the lid and moves the lid. If your hand just constantly slides on the lid, you're not getting that static friction. You need that static friction. Okay. Then you have kinetic. Kinetic means moving. And we're going to talk about kinetic. You've probably heard about kinetic energy and potential energy. And we'll talk a little bit about that as we go through these different sections. But kinetic friction, kinetic is to move. So kinetic friction is the force that resists the movement of two surfaces that are touching and are moving relative to each other. Okay. So like you move a book across your desk, same kind of thing. Okay. And the amount of static and kinetic friction between the surface of the desk and the book really determines how easily that book starts to move and then continues to slide. So static is when it's not moving, and then kinetic is when it starts to move. But how fast is it moving and so on, that is really depending on, again, what the surfaces are like. If they're both really smooth, then things slide across it really, really easily. There's very little static friction, but there's kinetic friction because it's actually moving. Okay. So you're like, okay, well, those are some really great places where friction is really helpful, but where, Mrs. Stewart, is friction harmful? Well, that comes more into play. Let's think about driving cars. None of you drive cars, but your parents drive cars and you ride in cars, okay? And I don't know if your parents are very hands-on with their cars or if you are hands-on with helping your parents with the cars, but your car needs something called oil in it. And there is a reason that we need oil in it. And it's called, oil is what's called a lubricant. And what lubricant does is it reduces friction. So, again, I'm not sure if you guys know much about cars, but cars are fascinating if you really want to understand the mechanical aspects of it. But there is a lot of moving parts in cars, lots of moving parts, and they move very fast. Think back to when I had you rub your hands together, and depending on how fast you rubbed them and for how long you rubbed your hands together, your hands got warm. Think about that on an exponential level inside of your car. Fast moving, okay? That RPMs is rotations per minute, I think. And sometimes it's going to be thousands of rotations per minute. Again, I don't know if you know anything about cars or the dials on the front of it and whatnot, but if you did not put oil in your car would catch on fire, okay? Because the static between the moving parts would create heat that would eventually create a spark. So it is imperative that you put oil in your car. You even put oil on your bikes. Okay. There's, things kind of get stiff there and you're like, oh, I got to lube this up. If you've ever watched The Wizard of Oz, not my favorite movie. I'm sorry if that happens to be your favorite, but the Tin Man, what happens? They have to carry an oil can because it gets all stiff, right? So that is kind of friction. They have pump a little oil in there and then he can move again. Same concept. The oil is a lubricant and allows things to move. If you've ever played air hockey, it's a lot easier to play air hockey when you've turned the table on and there's now air, right? That air becomes a lubricant and allows the puck to glide very easily across the air hockey table. So keep those things in mind. I said we're going to do just maybe play around with a little bit. Watch those things. Think about as you go through life, when am I using static? If there was not friction, when you use friction, if there was not friction, when you took a step, you would fall down every single time you placed your foot on the ground. The friction allows your foot, your shoe to grip. If any of you play any kind of sports, you notice that sometimes there's different shoes for different sports. And the soles of those shoes are different. They are designed to have the maximum static friction or kinetic friction to help with that sport. My oldest Sebastian is a runner. He has spikes for when he runs on those tracks. He's got very specific cross-country track spikes and he's got very specific cross-country spikes and very specific track spikes. Guinness is my thrower. He has throwing shoes. They don't have spikes because he has to be able to spin to throw the discus or spin and throw the shot put. So his shoes have much, much less, stuff on the bottom of their shoe that allows that. So it reduces friction that allows him to spin. He could not run on the track with those. He'd fall down. And Sebastian could not spin and throw with metal, spikes sticking out of his shoe. So there are different, shoes designed to help you with certain things. There's a reason if you've ever gone bowling, you put different shoes on when you go bowling. Okay. You need a certain shoe type on the bowling floor. Okay. Does that make sense? So and it all comes down to this, to friction. So a friction-like force that opposes motion of an object in a fluid is called drag. If you've ever done something like this in this picture, you're in a boat and you put your fingers in the water, you can feel that water pushing up against your hand. That is called drag. Drag also works against the forward motion of a bird or an airplane as they move through the air. Okay. So, I said, so like waving your hand, even waving your hand in air creates drag. You probably don't feel that much. If you wave your hand right now in the room, you're not going to feel drag. Okay. The air molecules are moving around pretty quickly, pretty easily. Okay. You were to put your hand in water, you feel that. Okay. That is still a type of friction. It is acting directly on your hand. It is touching the air, touching your hand. The water is touching your hand. Okay. As you swim in water, you feel the drag on you. Okay. I've never swum anything else other than water, but you see sometimes in those silly shows and they put you in like pudding, or I'm sure I've seen things on like, if you ever gone to those, like those where you jump in those ball pits, it's a lot harder to move through those ball pits than it is to move through water. There's more drag and resistance of you moving through that material. Okay. But also a force can act on an object from a distance. Okay. So it can act, from a distance, which means it's not directly touching it. Gravity is this. Gravity is amazing. Gravity works at the same rate as you guys saw on that video. If you were to drop a bowling ball and a feather off of a bridge, they should fall at the same rate because gravity is constantly pulling something to the earth at the exact same rate. 9.8 meters per second squared is the gravitational pull on Earth. But things like friction, which in that case, and drag, which is air resistance, is making that feather fall much, much slower than the other one. And people so often think, well, it's because the bowling ball has that larger mass, it weighs more. But he showed you with the umbrellas, 2 exact umbrellas, one open, one closed. One fell slower than the other. So it has nothing to do with the mass. It has everything to do with things like friction and drag, air resistance, all of those things. Okay. There's a reason why paper airplanes, some of them fly well and some of them don't fly well. We practiced with all of those paper airplanes beginning of last year. Had a lot of fun with that, building our airplane models. Okay. Again, some flew well, some did not fly so well. They all had the exact same mass because they were all made of the same type of paper. So gravity is the force that acts from a distance. When you jump up, it pulls you back to Earth. When you jump, you do not have to worry that you are going to fly away. You are going to come back to the Earth because gravity is constantly pulling you down. The magnetic force acts as a distance when the opposite poles of 2 magnets pull each other. If you take magnets and you hold them close to each other, but you don't have them touching, you can start to feel them wanting to pull each other. If you turn those magnets around, or turn one around, and you have both of the same poles facing each other, you can literally feel the magnets trying to push each other away. Okay. If you have any magnets hanging up on your fridge, then the magnet is not touching the refrigerator, it's touching the paper. The paper or the picture or whatever is between the magnet and the refrigerator. So the magnet is not touching the metal refrigerator because there's something in between the two of it, but it is still working. The magnetic force is pulling, is kind of squishing that paper. It's holding that paper in place. Magnetic force also acts as a distance. I said when they push each other apart. And we are going to, hopefully, I gotta make sure that our test tubes at school can actually fit nicely into the top of a bottle, and we are going to actually get to see these magnetic forces at work. Hopefully, that's if I can make sure they fit. So there are something called a field. And a field, when a force acts at a distance, the area in which an object experiences that force is called a field. So think about the magnets. There comes a point where the magnets no longer are pulling towards each other or pushing away from each other. You have pulled them outside of their ability to be magnetic to each other. Okay. The stronger or the larger the magnet, the stronger that magnet is. But some of our forces that have fields is the electric field, the magnetic field, the gravitational field. I love when science, movies like, oh, there's a force field around it. Okay, what force? Is it if you have an electrified fence around your yard, that's technically a force field because electricity has a force, and so on. But again, in those movies, it's, I don't even know what it's made out of most of the time. They don't even tell you what it's made out of, but it deters anything from getting inside. But forces, I told you at the very beginning that forces have a size and a distance. So a magnet has a magnetic field surrounding it, but it lessens as you get further away from the force. So when you talk about gravity, as you move, if you ever become an astronaut and you decide to go live on Mars, because who knows, by the time you guys get old enough, there might be people might be living on Mars. That's because that's, supposedly the goal. As you move away from Earth has less pull on you. It has less gravitational force on you because you are further away from it. Okay. You are smaller. I taught you guys about the seasons last year and the moon, and we talked about how the moon stayed in place because of where it is and the gravitational pull of both the Earth and the sun. The sun is gigantic, remember? So the sun is pulling everything towards itself, but because of where the object happens to be in space, it's just going to stay there. Okay, it's not going to get pulled any closer. Now, if we moved a lot closer to the sun, then we might get pulled into the sun, okay? Because then gravity's going to take over and it's going to pull, okay? But the moon stays where it is because we have a gravitational pull on it, and so does the sun. But we're closer to the moon, but we're a lot smaller than the sun. So that is why the moon stays in its orbit around the Earth, because of gravity. Fields are measurable and can have motion. So these are important things to remember. So electric fields. An electric field surrounds every charged object. You're like, what is a charged object? We're going to get really sciencey here. Charged objects come down to their atoms, the atomic structure. Think all the way back to your atomic structure. There are 3 parts: protons, neutrons, and electrons, right? Electrons travel around the atom, the nucleus, because the nucleus inside has the neutrons and the protons. And remember, protons are positive, neutrons are neutrons, electrons are negative. Charged particles simply mean, so an atom, a normal everyday at rest atom, is neutrally charged. Is not positive, it's not negatively charged, because the protons and the electrons balance each other out. For every positive you also have a negative. That makes 0, right? If I have 5 positives and 5 negatives, I still have 0. That is how atoms work. But as soon as I take an electron away, because I can't take protons away because I now have changed the element. If you remember that, all that stuff, the protons inside of the atom tell you what kind of tell you exactly what element is. If you look behind you or next to you, the periodic table of elements, that atomic number is telling you how many protons there are. That number also matches that also matches the electrons. But as soon as I take an electron away or I add an electron, I have changed the charge of that atom. If I take an electron away, I have now made that atom positive. If I add an electron, I've now made that atom negative. Okay, that is a charged. If I take something and I change the electrons in it, I have charged that object. Okay, charge that object. That is what electricity is. Electricity is simply the transferring of electrons. You see at the electric, you see at the beginning of this word. Sorry, I did not mean to change that page. Electric looks a lot like elect, and you just simply change IC to ON and you have electrons of electric. Okay, so the electric field around a charged object pulls oppositely charged objects toward it and repels like charged objects. You guys know that. It's a magnet. Okay, but the reason those magnets are like that is because the stuff it's made out of, and all the way down to the atomic structure. Okay, and then so then we have what's called static electricity. And you can see the effect of this. So if you've ever taken a balloon and you rub it on your hair, it looks like this person's hair. If you've ever gone to COSI and you touch that really big thing there, and then all your hair stands up, and then you can hold someone's hand and their hair stands up, it's because electricity is running through your body. It's not hurting you because there's different types of electricity, and you can make so on and so forth. Okay. That's really exciting, but you can see the electricity there. And so it has a field, but eventually, as that electricity goes, you'll notice that the person on the end, their hair may just slightly be standing up because the electricity is kind of, the field is a little further, that person's a little further away, so it doesn't have the same intensity as if something were closer. And we're going to go into a lot more depth into all of these. Each of these have sections. This is just a brief overview. Then we have magnetic fields. Isn't that pretty? This is iron filings. And if you were in my science exploration class last year, we did this, and we tried to kind of almost imprint a picture onto some blue paper. But what's happening is there are magnets, a magnet underneath here, and the iron filing is being pulled to those poles. So a magnetic field exists in the area around a magnet. Okay, and it's where the magnetic forces can actually act on that object. If you look on page 411 there, that's what I want us to try to do so we're going to get a test tube. We're going to take a bottle and we're going to fill it up with like vegetable oil. We're going to put iron filings in it. Then we're going to put a test tube in it. And then inside that test tube, I'm going to put a magnet. And you're going to see the iron filings like literally move through the oil and attach themselves. And it's going to look like that. But again, I got to get that set up and I have to make sure that our test tubes work. So that's really, really cool. But so if you take a look at that, the iron filing suspended in the liquid form lines around, this is called a cow magnet. There's multiple types of magnets. Okay. These lines can be drawn to show the magnetic field and are called magnetic field lines. The closer together the field lines are, the stronger the magnetic field. Again, so take a look at this picture up here. There's a lot more at this end, these two ends, than there are in the middle. That means the magnetic force is stronger here. Okay, do you see again how even in this one, they're darker here, but then they get a lot more faded out? That's because the magnetic field is not as strong out there. Okay. The magnetic lines, the lines are closer together at the poles than they are everywhere else. A magnetic field surrounds every single magnet. Because of these magnetic fields, paper clips, iron filings, things like that are then pulled towards the magnets. Why you can hang things on your fridge. My whiteboard's up front. The one on the left is magnetic. The one on the right is not. I had to ask for a magnetic one because neither one of mine were magnetic. And so I was able, that way I can actually hang things. I've got some magnetic stuff I want to be able to put up on the board. And I couldn't do that because I didn't have stuff up there. Okay. Then we have gravitational field. An object with mass creates a gravitational field around it. I have told you guys before, whether you remember it or not, every single thing on the planet and in the universe, if it has mass, it has a gravitational pull. You have a gravitational field around you, but you're really small, so you don't do anything. Okay. The pencil in your hand has a gravitational field, but it's really, really small, so it doesn't do anything. You got to be like moon sized almost to really start to have that gravitational field. So the gravitational field is the area surrounding an object in which another object could experience a force of gravitational attraction. The reason we can stand on Earth is because of its gravitational field. You go to the moon and your weight is 6 times less because the gravitational field is 6 times less than that of here on Earth, which is why the astronauts kind of like bounce a little bit. They still come down back to the moon because there is still gravity on the moon. It's just a lot less. Okay, and we measure gravity in that's weight. Okay, so that's what I said. You can lose weight when you go to the moon, but you still have the same mass when you go to the moon. Okay. Field lines can be used to show, again, the gravitational fields. The strength of a field is modeled by the density of field lines. Density, how many are in this amount of space. Remember, mass divided by volume. How much stuff is in a certain amount of space. That is density. Okay, so equally spaced field lines model a uniform field. The field line pattern below, so below on 411 there, shows the gravitational fields on the Earth and the moon. Okay, you see that? So they're evenly spaced. So even this one here, look, they're all evenly spaced, but they seem to be a lot closer together here than they are out here, right? So here, there's going to be a lot more gravity. But as I move away from the Earth, there's less gravity, okay, pulling on me because I'm further away from it. So I told you earlier that everything has forces acting on it. That may make things stay still, and that may make things move. Because things are always pushing and pulling on you. And you can move because you've overcome those forces. So another force is greater than that current force. So how do we figure out what these are? So usually more than one force is acting on an object. Right now, gravity is acting on you because it's holding you to the planet. And friction is at work because you're sitting in a chair right now. So right now you've got multiple forces working on you. Okay. Probably don't really have a magnetic field around you. And unless you're currently like shuffling across carpet and going to go touch the doorknob, that's where static electricity comes from. You're probably not really feeling an electric field. But the combination of all of these forces acting on an object is what we call a net force. When forces act in the same direction, you simply add them together to determine that net force. When forces act in opposite directions, then you subtract the smaller force from the larger force to determine the net force. So over here, got this boxcar, and it's moving. Sorry, I could not get the picture to all fit with all my numbers, but we can figure it out. So this is moving 60 newtons to the right and 30 newtons to the right, which means that it's moving 90 newtons to the right. So like yesterday, we went to the zoo, but Coral had to be in a wheelchair. So we pushed her in a wheelchair. So I was pushing her, but my 4-year-old nephew was like, look, Aunt Nikki, I'm helping. Okay, he really wasn't that much of a help, but he was also pushing the wheelchair. So the two of us together were pushing Coral in the wheelchair. So we would have added those together, okay? But at the same time, there were times where it was harder to push her than other times. My mass didn't change. Her mass didn't change. But something was pushing against us. And that could have been a variety of things. Pushing her up a hill made it a little bit harder because gravity was working against us. Friction was also working. Sometimes parts of the sidewalk at the zoo is a little rougher than others. So those forces were pushing against me as I was pushing Coral forward. I was winning. So the force, so let's say that I was moving 50 newtons, and the stuff working against me was the 30 newtons. The object then would have been moving 20 newtons to the right because I was working. So I was able to move forward and overcome the forces working against me. Does that make sense? So take a shopping cart. If you put a lot of stuff in it, it's really hard to potentially push around the store. Completely empty, you can push it around, no problem. My 4-year-old nephew could help push it around, okay? So the net force acts in the direction of the larger force. I was the larger force working against gravity and working against the friction of the ground. So my force was strongest, so we were moving in the direction that I was pushing Coral in the wheelchair. But sometimes the forces can also be balanced, okay? When the forces on an object produce a net force of 0. So think back almost a couple months ago now, when we had that pep rally with the tug of war. Tug of war is a great example of this. There were many times where it seemed like neither side was moving. The net forces were 0. The left side was equal to the right side. But as soon as one group started moving more, we went from net force 0 to net force whatever we would have measured the newtons in, would have measured that force in. Okay. And then it was going to the left or to the right. But balanced forces will not cause a change in the motion of a moving object or cause a non-moving object to start moving. Which means that an object can be moving and a force is applied to it and it continues moving, but nothing changes. So do not think that a net force of 0 means no moving. If an object is already moving and then a new force is applied, but it balances out another new force potentially, then it's still going to be 0. But something is winning because it's moving. So yeah, net force is usually going to be 0 net force. Really, I'm like seriously trying to, my brain is like thinking of a situation where net force is going to be 0, but the object is still moving. I can't think of anything right now, but if I do, I will let you know. So as of right now, net force being a 0 net force means that the object is still, because everything acting on it is equal. Okay. Oh, sorry. But you can have, like, I guess, additional net forces. Like if you put 2 new forces on and they balance each other out, then the object isn't going to change what it was already doing. So a lot of objects around you right now have balance forces acting on them. I chose this picture here because these lights are hanging from the ceiling and they are at a beautiful balance right there. Okay. Because the light hanging from the ceiling does not move. It's there. It's really good. It's good because I don't want it to fall on us all the time. Because the force of gravity is pulling the light down, but the force of the chain that is attached to the ceiling is pulling it up. Okay. So this is a balanced force. Gravity's pulling it down. The cord is holding it up. But forces can be unbalanced. When the net force of an object is not 0 in, the forces are unbalanced. Tug of war right there. Okay. Sometimes it takes a little while to get that 0 in to not be 0 anymore. But even if it's 0.5 in or 1 in, that is still unbalanced and there is still movement, even if it's just slight. Okay. Unbalanced forces produce a change in the object's motion. It could change speed or direction or both. The change in motion is called acceleration. And acceleration is not always in the direction of the net force. You're like, what? We'll talk about that. Okay. And here's another time where the words that we use in science does not match the words that we use in everyday speech. When we think of acceleration, we think of going faster. Acceleration simply means change in speed, change in motion. So when I slow my car down, that is acceleration. But we call that negative acceleration or deceleration. But it is still falls under the umbrella of acceleration because the true scientific definition of acceleration is just change in motion. Okay. We'll also talk about change in direction is all part of this as well. Okay. So acceleration is not simply speeding up. Acceleration is change in motion. Okay. Okay. So even in tug of war there, the group that pulls with the greater force, acceleration is going to go towards the group of greater force. So now we're going to dig into Newton's first laws. I'm not really going to dig into them a whole lot, but Newton was amazing. Okay. Newton's first law is this. It's probably one that you have all heard and probably could repeat. The law states this: an object at rest stays at rest, and an object in motion stays in motion at the same speed and direction unless it experiences an unbalanced force. You often hear me say an object at rest stays at rest, an object in motion stays in motion at the same speed and velocity, unless it is acted upon by an unseen force. So Newton's first law describes the motion of an object that has a net force of 0 in acting on it. Okay. So an object at rest is going to stay at rest unless something comes and moves it. An object in motion is going to continually stay in motion theoretically until something stops it. But because we live on Earth, We have something called gravity. We have things called friction and air resistance and drag and all that kind of stuff. When you kick a soccer ball, if you were to kick a soccer ball in outer space, that soccer ball would go on indefinitely until it ran into another planet or an object or hit a gravitational field. It would go on for eternity until something acts on it to make it change direction or speed or stops it. We don't get to see that here on Earth because if you kick a soccer ball on the field, it's going to slow down because of friction against the grass. If you kick a soccer ball on ice, it's going to go for a lot longer, but there's still some friction at play there. Okay, so that is Newton's first law. An object at rest stays at rest. Newton's first law is also called the law of inertia. I know that you guys have heard me say this. Inertia is the tendency of all objects to resist a change in motion. The best way to picture this, the best way is you are sitting in your car with your parents and you are driving, and all of a sudden your parents slam on the brakes and you fly forward in your car. Okay, but your seatbelt catches you because that's why you wear seatbelts. It's really important that you wear seatbelts. The seatbelt catches you, and so, but you are moving forward because your body is sitting in the car and it wants to continue moving. It wants to continue. Your object at rest stays at rest. Again, if you're sitting there and your parents accelerate real fast, you kind of move back into your seat again because your body was at rest. It doesn't want to move until something forces it to move. Okay. An object in motion stays in motion. So again, here's where that car comes into play. Your body sitting in that car wants to move at the speed that it is going. You are going, your body sitting in a car driving 60 miles an hour down the highway. You are not moving sitting in the car. Like your body, you're just sitting there. You're like, oh my gosh, I'm so tired of sleeping. But your body is still moving at 60 miles an hour because you are in an object that is moving 60 miles an hour. If you were to suddenly hit something, your car were to hit something, your body still wants to travel at 60 miles an hour. That's why it hurts. If you've ever been in a car accident, that's why you may have bruises from your seatbelts. That's why the impact of the airbag hurts. Your body still wanted to be moving in that direction. That is why it's important that you wear a seatbelt, because if you don't wear a seatbelt, then nothing else is stopping you from going into the front of the car or the windshield. And sometimes even the windshield does not stop you, and you go through that. I know that sounds awful and scary, but it is the truth. And it is because of this law of motion. Your body is in motion. It wants to stay in motion until something stops it or changes its direction. That is why it is important. This is Mrs. Stewart getting on her soapbox talking about safety. That's why you wear a seatbelt in the car right here, because you can't predict that something isn't going to happen and that your body is not going to continue moving. If you're driving 10 miles an hour, you might lean forward a little bit. It's not going to be bad. But you on that freeway traveling at high amounts of speed, your body, even though you are sitting in the car and you're talking with your family or your friends and goofing off, your body is still moving at the same rate of speed that your car is traveling in. Does that make sense? That is inertia. Okay. That is why you fly forward and your seatbelt catches you, is because your body is moving at that speed. Okay. When your car accelerates and you're pushed back into it, or you're at a roller coaster and you're pushed back into it, it's because your body was sitting there. Your body wanted to stay sitting there, didn't want to move. But then suddenly you are quickly moving fast. Your body takes a second to have to catch up because it was still sitting still. Same concept. It is the law of inertia. Okay. So after all, an object at rest has a velocity, just happens to be zero. And you're like, well, what is velocity? Well, velocity is an object moving, it is a speed and a direction. So velocity has to have both. I am traveling at 60 miles per hour south, or I am going 25 miles per hour right. That is velocity, speed, and direction. What is Newton's second law of motion? It's when unbalanced forces act on an object, the object accelerates. There is actually an equation for this. The acceleration of an object depends on the mass of the object and the amount of force applied. Again, the easiest way for me really to visualize a lot of these concepts is to think of driving. If you are at a stoplight, you are in one lane, there is a semi-truck next to you. The light turns green. Who accelerates faster? Your car, whatever car it is, whether it is a minivan or a Mustang or a Maserati or whatever, it's going to accelerate a lot faster than that semi. Why is that? Your car is smaller, okay? It's taking a lot more force to make that truck move as fast as your car is moving, okay? That's why you often probably see your parents move into a lane that's not behind a semi stopped at a red light, because it's going to take a lot longer to move because that semi just has a larger mass. The same concept applies on when stopping. There is a reason that when you guys learn to drive, that there is a safe distance between you and a semi. They cannot stop on a dime. They cannot brake as fast as your car can. There is a lot more mass to that object. It's going to take more time for that object to stop. Does that make sense? This is an equation for this. So objects with different masses are going to have different accelerations if the same amount of force is used. So again, that should say cart, not card. I'm sorry. And I was typing this yesterday. When the cart is empty. Oh my gosh. Again, so think about that. If you go grocery shopping with your parents, you're at the beginning, you're like, I'll push the cart. Halfway through, you're like, I'm done pushing this cart. In order for your cart to move at the same speed throughout the store, you must push it harder. You have to push the cart with more force to make it move. So it is because the mass has increased. If I want the same acceleration, and my masses are different, my forces have to be different. Okay. So force equals mass times acceleration. F equals ma. This is an equation. Remember it. You're going to use this a lot in physical science, and then when you get into physics in high school, so think about it now. So Newton's law links force, mass, and acceleration. F is force, m is mass, a is for acceleration. F equals ma. You can rearrange this equation to figure out mass or acceleration. If I give you the force of an object and the acceleration of an object, you can figure out how much the mass is, okay? The equation tells us that a given force applied to a large mass will result in a very small acceleration. Okay? Again, think of that semi-truck. It doesn't accelerate very fast because it's gigantic. Okay? It's gigantic. And it's only got so much force. I mean, you can't get a semi-truck to 0 to 60 in a couple seconds. It's not possible. Okay? I don't even know what force that would require. Okay, you would have to really figure that out. I mean, it would have to be huge. But you could figure that out because you'd put the mass of the truck, that acceleration, and then you'd figure out the force. And it would be insane. Okay. When that same force is applied to a much smaller mass, the acceleration is going to be huge. Now, if I take that same force and I apply it to your car, oh my goodness, your acceleration is going to be insane. Then you have Newton's third law, which you probably heard without realizing it. Whenever one object exerts a force on a second object, the second object exerts a force on a second. Exerts an unequal and opposite force on the first. Somehow I wrote that twice. It should say the second object exerts an unequal and opposite force on the first. Okay. I feel like I typed that up wrong, so I'm looking really fast. Because that does not feel right to my brain right this second. Yes, that should say equal. So please, please, please fix this. Whenever, it should read this. Whenever one object exerts a force on a second object, the second object exerts a force, exerts an equal and opposite force on the first. So take off this whole middle section and change on equal to equals. I am so, so sorry. Yesterday was really, really chaotic. And I did not catch that. So please, it is. So what I'm trying to say is you've probably heard every action has an opposite and equal reaction. That's what this is saying. Every action has an opposite and equal reaction, which is why I knew that unequal was not right, because I was like, that's not sound right. When you push against a wall, Newton's law tells you that the wall is actually pushing back on you. You're like, what? I don't feel the wall pushing me. It's because it's equal. There's no movement. Okay. It's pushing on you. So please, please fix that. It's in the textbook on page 418 in italics at the top. So please, please fix that in your notes. I am so, so sorry. So objects exert force on each other. Newton's third law also states, as all forces act in pairs. Again, everything has an opposite and equal reaction. Whenever one object exerts a force on the second object exerts an equal and opposite force on the first. Look, there it is again, but that's actually correct. There are action forces and reaction forces. Action and reaction forces are present even when there is no movement. You sitting in your chair right now is Newton's third law. You are exerting a force on your chair when you sit on it, and your chair is pushing back up against you. That is Newton's third law in action right there. All forces act in pairs. Okay. So forces in pairs have equal size but opposite directions. These guys, these swimmers are all pushing off this wall. These look like, I don't know, some kind of, I don't even know. But they are pushing off of the wall here. And so they are having equal size forces, but they're pushing opposite directions. The person is pushing this way, right? They're pushing this direction, but the wall is pushing them this way. So when an object pushes against another object, the object pushes back equally hard, but the second object pushes back in the opposite direction. Okay. In a pool, the swimmer's feet pushed against the wall as he moves forward. This push is the action force. The wall also exerts a force on the swimmer. This is the reaction force, and it moves the swimmer forward. The forces do not act on the same object. Another thing is you staying on the earth. The earth is pulling you down. You are pulling the earth back to you. Opposite and equal. You can't feel that because it's really, really small, but it's happening. So this says when they are equal. Okay, equal in size. Sometimes they're not equal in size, like you stand on the earth. Even though action and reaction forces are equal in size, their effects are often different. Gravitation is a force between two objects. You have a gravitational pull. You are actually pulling the earth to you, but you are really, really small compared to the earth, so the earth doesn't really care. It's like whatever, right? If you drop a ball, gravity is an action force, pulls the ball toward the earth, but the reaction force pulls the earth toward the ball. But does the ball really move the earth? No. Okay, but does that mean the ball isn't trying its little hardest to pull the earth to it? No, because it is. It is. The force on the ball is the same size as the force on Earth. However, Earth has much more mass than the ball, so Earth's acceleration is much smaller than that on the ball. It takes a long time for that Earth to move, accelerate. You think a semi-truck is big? Think of the Earth. Okay? It's trying its hardest. If you go over and you're trying to push somebody who's a lot bigger than you, you're not, they're pushing against you as you're pushing against them, but you're just like hitting a brick wall because they're so much bigger than you. Okay. Guinness, my 16-year-old, he's thrower, so the kid can deadlift 400 plus pounds, so he's very, very strong. But he loves to like sit on the couch and be like, Mom, help me get up. I am of no use. I cannot pull my 16-year-old up off the couch. I can't do it. And he just thinks it's hilarious because I'll plant my feet and I'll start pulling. But what happens is my feet slip and then I fall on my bottom and he just thinks it's hysterical. And because he's just that his mass is that much larger than my mass. And it's really funny. But we're both acting. He's just sitting there. Gravity is at work, and I just cannot overcome gravity and his mass to accelerate him up. Okay. But he has no problem like picking me up and throwing me over his shoulder. Okay. So similar kinds of things here. Forces can act in multiple pairs. An object can have multiple forces acting on it all at once. When this happens, each force is part of a force pair. So, baseball. Asa, you love baseball, so you'll like this one. When a baseball bat hits a baseball, the bat does not fly backwards, does it? Nope. It keeps going. Okay. It follows through, right? It doesn't stop as soon as it hits the ball either. Okay. A force is exerted on the ball by the bat. The bat does not fly backward because the player's hands are exerting another force on the bat. What then keeps the player's hands from flying backwards when the bat hits the ball? The bones and the muscles in the player's arms exert a force on the hands. Okay, so there's like this chain reaction. If you weren't gripping, if you were just to throw a bat and a ball at each other, they would hit and they would go backwards. Okay, because their forces were acting on each other, and then the reaction was that they ended up going the opposite directions. But because you're holding the bat, and I don't know how many of you play baseball, but you feel that impact of that ball hitting that bat. Like you feel the vibration in your hands. Okay. And then it travels down your arms. And this is why right here. Okay. Exactly right here. So even a simple activity as baseball, swinging a bat and hitting a ball. I'm not talking about the whole game being simple. I'm just talking about this act right here. And it's not even, it's hard because that bat's not very big and that ball's not very big and trying to actually get them to hit. But when they actually do hit, there are so many forces at play. Okay. Okay. So that's the end of our just introduction to forces. We'll go more in depth in our forces in the next few sections. Okay. Oh, why can't I get this to stop? Sorry, guys. This is not